Hello, you guys. So we had a little controversy on the integral test because we were testing out the LRAM, the left endpoint Riemann sums, and then you're like, well, what about the right endpoint Riemann sums? That's going to cause a problem for us. So that's going to be an underestimate. So how can we really use the integral test? And you all bring up fantastic questions. Okay, so let's go through and talk about exactly what the integral test is. Okay, so the integral test is basically saying, let's say we have this particular infinite sum where f of n is equal to a sub n for n greater than or equal to 1. We assume that f of x is eventually going to be non-negative and decreasing because it could be doing anything prior to that. It's just that prior to that, it's still going to be a finite thing, okay? But eventually, it's going to be non-negative and decreasing, okay? Then we will say that a sub n, that this series, the infinite series, will converge if the integral converges, and then the infinite series diverges if the integral diverges. Now, when we say that this integral converges, that means that it's finite, that it has an actual value, that it has a finite value. Sometimes we know what it is, and sometimes we don't know what it is, as we've always talked about it. But this is finite, that it's converging to the x-axis fast enough that we can see what the heck is going on. This one over here is infinite, so if we add it up, that sum is an infinite thing, so we have no idea what the dealio is. So what it's basically saying is that if you compare the series to your integral, then however he's behaving similarly. So whatever he's doing, and that's all there is to it. So what I'm going to show you is I'm going to show you that we're going to do LRAM with this graph, and then we're going to do RRAM with that graph, and I'm going to show you how it all just kind of comes out beautifully in the wash. Because let's go back to what we know about LRAM and RRAM. LRAM is your left endpoint and moves on into the sunset and usually leaves out, quote unquote, the right endpoint. Now, RRAM is you start with the right endpoint and you move left and you lose the left endpoint. So every other term in between counts for both of them. So LRAM loses the last guy, RRAM loses the first guy. So keep that in mind when we're doing this, okay? Okay. So I'm just going to try to not butcher this picture here, but we're going to do the best we can. So we know we have in front of us a non-negative decreasing function. And our series only goes up by integers, so we're going to have to go ahead. Come on, Shar. So we're going to go up, and we're going to go up here, and then over here, and then over here. So I'm going to say that this is 1. We're starting 2, 3, 4. And I want to go up n, where this is a huge integer, and then this will be n plus 1. Now, if I use LRAM, okay, so this is LRAM, I'm going to go up to my thing over here, right? And because my series goes up by 1, that means the width of all the rectangles is 1, as we discussed in class. So you're saying to yourself, this is an overestimation, right? Oops, come on, over here, Shar, of what the, butcher, getting sloppy in your old age. Okay. So fill you in over here. So we're doing this, we're moving along and doing our thing, and then we get here, it's a slight overestimate and so forth. So these guys right here, these areas are contingent upon the value of the first term here for this guy, right? So this is basically the sum of what a sub 1 would be. And I'm going to change the color so we can see how pretty it looks, okay? So this is a sub 1 here. This is a sub 2 because it's dictated based on the height of that rectangle, a sub 3, and then we come down here and that's a sub n, right? Now you guys are looking at this and you're saying this is an overestimate, right? Like, okay. So we are going to come on up here and we're going to say then that the sum as n equals 1 to n is of a sub n is greater than or equal to the actual area, right? The actual value of the integral under this curve, if you will, right? So that's going to be 1 to n plus 1 because that's basically saying we're just doing a finite limit there, okay? So of f of x dx. And that's true about that one, okay? So now what I'm going to do is I'm going to go over to the other side because this is where all the controversy came along and then the bell rang and you guys got all verklempt and all that. So we're going to go ahead and this time we're going to start at n minus 1, 1, 2, 3, 4. It's hard to write. Okay, so if I start from the right and work my merry way left, right, I'm going to go here, go across, start over here, work my merry way across, start here, work my merry way across, start here, and work my merry way across. You guys are all like, yes, this is an underestimate, Seashwa. This is an underestimate of what the actual value of the integral is. Okay, well said. So here's the thing. If I come over here and I look at this rectangle and I want to find the area of that rectangle, the area of the rectangle is the width, which is 1 times the height. And the height at that point is a sub 2, right? Because it came from the second term's value, okay? Then over here, this is going to be a sub 3, a sub 4, and over here we're still at a sub n. Now this time, this sum is an underestimate of the value of the integral. So we're going to come on over here, and we're going to say that this sum of a sub n, of n equals, we're at 2, exactly, because we're starting at 2 here because the height was contingent upon the second term, okay, to n, is going to be less than or equal to the integral from 1 to n of f of x dx. Okay? Because again, we're estimating, so this starts at 1 and goes over to n for the integral. Now, the cool thing is that there's some funky inequalities going on here. Now, the problem is that this guy starts at 2, and we're missing a sub 1 here on this guy, because in order for me to write this as one big inequality, I got to make sure everybody matches up. So this guy contains a sub 1. This inequality does not. So what do? We add a sub 1 to both sides, okay? Of n of a sub n is less than or equal to a sub 1 plus the integral from 1 to n of f of x dx. Now, if you look at this, if I have a sub 1 here plus this, what I could do is merge this into one big sum and just start it off at 1. So now I know then that I can say that n equals 1 to big N of a sub n is less than or equal to a sub 1 plus the integral from 1 to n of f of x dx, right? Okay. Now the beautiful thing is I am going to take this guy, and we're going to merge them into one big inequality. And I'm going to pause, and I'll see you in a moment. Okay, so I combine this as one big inequality. And the cool thing is that this series is somewhere between this integral and a sub 1 plus that integral, right? So if I take the limit as n approaches infinity of the integral, this guy right over here, if I'm going to throw it right up in the front here as n approaches infinity like so. If I take the limit as n approaches infinity of that entire thing, right? Then what does that tell me? Well, here's what it tells me. That infinity plus 1 is still infinity, so the integral from 1 to infinity of f of x dx is less than or equal to, now since n is approaching infinity, this finite series has now become infinite. The sum as n equals 1 to infinity of a sub n is less than or equal to a sub 1, which is a finite number, and then to the integral of 1 to infinity of f of x dx. Okay? Now let's take a look at what that's saying to us, right? Let's take a look at what that's saying to us. This series is squeezed somewhere in between here and here, right? So let's say, for example, if this series is finite, right? So if this series is finite, let me change the color. Let's go with orange because we haven't used that. If this turns out to be a finite series, then we know it converges. Yes? I hope you said so, yes. Okay? That means it converges. If you look over here, that means this series converges. This is a finite number plus a, that's not a finite series. You know what? I'm not going back because that's just crazy. Okay, that this is finite, I mean to say finite sum, right? It's a finite, it's going to come out to some kind of a finite number and it converges. I almost butchered that one, you guys. And converges, okay? So we know that this is finite, that we can actually find a sum for it, okay? Then this guy over here, all we have is a finite number plus something finite is still finite. And he's stuck smack dab right in there, right? So If he's going to be finite, well, then he has to be finite. Now, conversely, is that the right word that I would use here? Conversely, okay. What did that just do? That was weird. Okay, so conversely, let's say that the integral diverges. Let's say that the integral diverges as I sit here and try to erase like a schlep. Okay, let's say that the integral diverges, that this guy diverges, right? Then this guy here is going to be a finite number plus something that diverges. It still diverges, right? So finite plus diverges still diverges. So if your series is stuck in between there, it's basically like a little squeeze theorem action, then it's basically saying that he is going to diverge also. So it does satisfy the conditions that however the integral behaves, the series is going to behave the same exact way. And again, you guys, it comes from the fact that when we were calculating LRAM and RRAM, right, this took away the last endpoint. This took away the first endpoint. Now, because this thing, and you're saying to me, like, well, LRAM, it loses the last term. We're never going to lose terms because this thing goes on forever and ever. And RRAM is simply the first guy that gets kicked out of the picture, which is him right here, okay, which is finite, right? So finite plus diverges is diverges. Finite plus converges, converges. So it basically goes to show that when you're doing RRAM, which is this guy right here, and then this is LRAM, which is this guy over here, or do I have it backwards? Either way, no, this is LRAM. This is LRAM here, right? And then this is RRAM over here, right? It's basically saying that they are going to merge with the exception of the first term, yes? And whatever the integral does, the series does. With that said, I hope this was helpful to you guys. I hope it cleared up some stuff for you. And again, it just comes through. The little squeeze theorem action comes into play. And the idea, again, as I keep reiterating myself, which is almost like to a fault and to like annoyance, actually, is that hold on a second. I just paused it for a second, but I just want to say hi. I hope you guys got a little something out of it. The cool thing is that with this, it does tap into the connection between left Riemann sum and right Riemann sums and how the only difference is your first term when you go off to infinity. So again, I think it should do enough to satisfy your, taste for like, oh, well, what if it's under? Then, it's all just going to come out in the wash anyway. Okay? So I'm going to say done, and hopefully you'll get something out of this, and you know that homework is on its merry way. Ask me my favorite color, or you should be able to tell me that my favorite color at this stage as we speak is turquoise blue.